Okay, atomic absorption spectroscopy. If a solution containing a metallic compound is aspirated into flame, a vapor which contains atoms of the metal may form. Most of these gaseous metal atoms will remain in the ground state. These ground state atoms are capable of absorbing radiant energy of their own specific resonance wavelength. Hence, if light of resonance wavelength is passed through a flame containing the atoms, then part of light will be absorbed, and the extent of absorption will be proportional to the number of ground state atoms present in the flame. This is the underlying principle of AAS. If a light of resonance wavelength is passed through a flame containing the atoms, then part of light will be absorbed, and extent of absorption will be proportional to the number of ground state atoms present in the flame. This is the underlying principle of AAS. In AAS, as with the molecular absorption, the absorption A is given by the logarithmic ratio of intensity of the incident light signal I naught to the intensity of transmitted light IT. That is A equal to log I naught over IT, KL N naught. N naught the concentration of atoms in the flame, number of atoms per ml, and the path length K constant related to absorption coefficient. The procedure by which the gaseous metal atoms are produced in the flame may be represented. Solution nebulization and produce mist, evaporation, solid, vaporization, gas, dissociation, metal, gas, and halides, X, absorption of radiant energy, metal plus gas. In the above simplified energy level diagram of atoms, inert represent the ground state in which the electrons of given atoms are at their lowest energy level, and E1, E2, E3, this represent the excited energy levels. The transition between two quantized energy levels, say from inert to E1, E2, corresponds to the absorption of the radiance energy, and the amount of energy absorbed is determined by the Bohr's equation, delta E to E1 minus E naught Sv Sc over lambda, where c equal to velocity of light plus Planck constant, the frequency of the radius unobserved, lambda wavelength of radiation observed. Instrumentation, hollow cathode lamp, atomization, atomizer flame, hollow cathode lamp radiation, and atomizer, nebulizer. monochromator filter, detector, recorder. Also, we can represent the basic instrumentation of atomic absorption of a spectrometer. Also, you can recognize in the block diagram showing the components of atomic absorption spectrometer. Light source or radiation. The primary need of the light source is to generate a narrow line profile with a minimum background. It should also have a reliable and reproducible output with enough intensity to provide a high signal to noise ratio. In atomic absorption spectroscopy, generally two types of light source are used, that is hollow cathode lamps and electrodes less discharge lamps. Except for analytes such as arsenic and selenium, hollow cathode lamps are the most typically employed, while electrodes less discharge lamps are used less frequently than hollow cathode lamps. Light source. Chopper. The light source should be modulated and mechanically chopped to differentiate between the light from the source and the emission from the sample cell. Chopper distinguishes between the absorption and emission signals. It is situated between the light source and the atomizer. Nebulizer Born system. It produces a mist of aerosol of the test solution. That is, it converts the test solution to gaseous atoms. It soaks in the liquid samples at a controlled rate and produces a fine aerosol spray for use in the flame. It effectively combines aerosol fuel and oxidant. Atomizer. Atomization is the process of separating particles into individual molecules and breaking molecules down into atoms. This is done by heating the analyte in the flame or graphite furnace to high temperature. To generate atoms from a sample, two systems are usually utilized. Aspiration involves soaking a sample solution into a flame, whereas the electrothermal atomization involves placing a drop of the sample into a graphite tube that is subsequently heated electrically. Some instruments include both atomization process, but only have one pair of light. After selecting the suitable lamp, it is directed towards one or more atomization systems. Monochromator prism. A line isolation device is necessary to ensure that only light of wavelength specific to the analyte of interest is measured. A monochromator is the line isolation device utilized for atomization absorption. All wavelengths of light enter the monochromator through an entrance slit and are subsequently divided into specific wavelengths using a prism, or more typically diffraction. It isolates a specific emission from the other lines, separates the resonance line from all non-absorbed lines generated by the radiation source. By adjusting the position of this dispersing device, only light of this desired wavelength enters the detector through the exit slits. Since atomic absorption is a specialized technique, very highly resolving monochromators are not required. Detector. The monochromator selected light is directed onto a detector. This apparatus converts radiant energy into electrical energy and giving an electrical signal to the radiant absorbed by atoms. Typically, a photomultiplier tube is used as a detector. Its function is to convert the light signal into an electrical signal proportional to the light intensity. AC amplifier, the electric current from the photo multiplier detector is fed to the amplifier, which amplifies the electric current several times. Recorder readout device. It may be simple galvanometer or charge recorder digital display. See, application of atomic absorption spectroscopy AAS. The atomic absorption spectrometry technique is one of the most important instruments for detecting trace ppm and ppb metallic elements. This approach is used for the quantitative determination of approximately 60 metals. Atomic absorption spectrometry is useful in all areas of chemical analysis. The atomic absorption spectroscopy method is well established in analytical chemistry, ceramics, mineralogy, biochemistry, metallurgy, water supply, medicine, and soil analysis. Quantitative analysis. Quantitative analysis depends on the determining the amount of radiant absorbed by the sample. This measure provides the number of observing atoms in light world. However, the concentration of element in the sample cannot be calculated simply from the number of observing atoms and atomizer. In practice, quantitative measurements are usually depend on the calibration. Calibration curves are generated using the known concentration solution of the sample element. The sample is atomized similarly to the standard and its concentration is calculated using the calibration curve. Atomic absorption spectroscopy used for the quantitative determination of various metals elements. Metallurgical and inorganic analysis. The elemental composition of minerals and rocks provides important information on the commercial viability of mining activities in areas that have been studied. After mining, the ores and the minerals must be examined by composition for refining activities to the efficient. Similarly, trace metals analysis is extremely useful in the search for the oil and water deposits. Atomic absorption spectroscopy has been used to analyze trace metals in geological, biological, metallurgical, glass, cement, engine, oil, marine, sediments, pharmaceutical, atmospheric samples. It is also used to determine the trace elements in the ground surface water, rocks, ores, minerals, and so on. Atomic absorption spectroscopy analyzes light yellows almost completely. Atomic absorption spectroscopy is also used in the determine cobalt, chromium, magnesium, lead, zinc, and other elements in iron and steel. Pollution monitoring. Monitoring for the trace metals, pollution in the atmosphere, and industrial effluents, oceans, rivers, and lakes is critical for determining the safety of the living beings. Atomic absorption spectrometry is utilized in pollution analysis, such as lead in the atmosphere and arsenic in groundwater. Food and beverage. In the food and beverage industry, it is used for the analysis for various elements, concentration in wine, beer, and fruit drinks. Atomic absorption spectroscopy is also used for the determination of various types of contamination in food. Medical pathology, calcium, magnesium, sodium, and potassium levels in blood, serum, and plasma are determined by using atomic absorption spectrometry. Atomic absorption spectroscopy is used in the blood analysis for the determination of sodium, potassium, iron, copper, zinc, and lead. Atomic absorption spectroscopy is used in the hair nail analysis for the determination of cobalt, zinc, magnesium, lead, copper, and iron. Atomic absorption spectroscopy is utilized in the analysis of metals in food. Atomic absorption spectroscopy is utilized for the metal analysis in petroleum products and lubricating oils. Pharmaceutical industry, trace metal analysis is critical in the formulation, development, catalyst efficiency, and dose limit determination. Most elements have a helpful role in the specific prescribed limitation, but their impacts the hazardous beyond those limits. In the pharmaceutical industry, atomic absorption spectroscopy is used for the determination of trace elements present in the drugs. Biochemical analysis, atomic absorption spectroscopy is used in the determine sodium and potassium levels in biological fluids as well as cadmium and zinc levels in the industrial inputs. Urine. In forensic labs, trace metals analysis gives useful information on specimens such as stomach contents for food poisoning, paint chips, fibers, and hair strands gathered at the crime scene. For a material development, composition and trace metals have a significant impact on common material characteristics such as hardness, brittleness, grain size, stability, amorphous nature. Trace metal analysis can provide useful information on the performance attributes of such materials. Agriculture, atomic absorption spectroscopy is used to determine the presence of metallic elements in soil such as calcium, strontium, and cobalt. Additionally, it is utilized in the animal feed analysis for zinc, copper, manganese, calcium, potassium, sodium, and other elements. It is also used for analysis of animal fertilizer to determine concentration of calcium, copper, manganese, iron, and other elements. Selected determination by atomic absorption spectroscopy, magnesium, calcium, tap water, ethylene, vanadium present in the lubricating oil, trace element, zinc, copper, nickel, cadmium in the polluted soil, tin in the canned fruits juice, chromium in steel, arsenic in soil and water by hydride formation, arsenic soil and water by the hydride generation,